of x squared. Do you guys understand what this mapping is doing? Like, let me draw a picture, right? For points really close to where the length of x, so this is like length of x equals to 1, right? So what it's doing, right, is it's taking points here, right, and it's drawing them inward. That's not quite right. There's some place here. There's some radius, right? Well, let's see here. How about this? Let's just check this out. When's the length of this? Let me just work out something here right quick. When's this equal to 1?
Sorry, I was looking at the length of x.
It's all good. So we got length of x over the square root of 1 minus the length of x squared equals to 1. So that gives me length of x squared is equal to 1 minus the length of x squared, which means twice the length of x squared equals to 1. So apparently, the length of x equals to 1 over the square root of 2. That is the dividing line. So essentially what's going on here is if you were to look at that right there, right, if we look at this, 1 over root 2, that sphere is being mapped to the 1 sphere, right? Now, on the other hand, anything inside that, right, everything inside that is actually being mapped to inside the blue. Anything outside the red sphere is being mapped to outside of the blue sphere. So like if I could picture it, keeping in mind the red sphere, just for a second, inside the image of the red, maybe I should draw another one. All right, so like this mapping F, what it's doing, right, what F is doing is it's taking all of this and mapping it to here, okay? And it's taking all of this, and what's it doing? It's mapping it out here forever and ever and ever, all the way out. As you're approaching where you don't get to, the length of x being 1, the denominator is becoming super small, which means that the length of the vector is becoming really, really large. You're going to infinity. In this way, we take the open ball and we expand it to all of our n. All right? So that's what that map does. Is it a smooth map? Yeah, it's a smooth map because the place where it gets into trouble, you don't get to. Right? Like the length of x being 1 is you don't get there, so it's a smooth map. And how about g? G would be the inverse to this map, actually, and the formula for that is, do you guys care to guess? G of y equal to what? Man, I should have just made this a homework problem. It's pretty cool. 1 plus length of y squared. This takes all of our n and it condenses it into the unit ball. These are inverse maps. F is a diffeomorphism, G is a diffeomorphism, Rn is diffeomorphic to the n ball. So, yeah. Then the next example in this is just that, and the next example is kind of more silly, which is just that if you have a M manifold and you have a chart domain U, M is diffeomorphic. So here's M. any chart domain U, you can prove that M is diffeomorphic to U. Ah, thank you. What's the diffeomorphism? Yeah, I'm actually, I don't know for sure, but let's see here. So this would take you to phi, which takes you to what? Like phi of U, which is an open subset of Rn, right? And why is that a diffeomorphism? So let me ask a kind of trippy question. What's the local coordinate representative of this map? See, let me draw this in a slightly different way. Here's M, right? Over here is phi of U, right, which is a subset of Rn. I'm actually thinking of the chart as the mapping we're studying the smoothness of, right? So what's the local coordinate representative of a chart then, from this perspective? If this point is P, it's inside the chart domain U, right? I can look at, well, let's suppose that this is, phi 2, which is also a chart domain there, right? That goes down here to Rn. And of course, this is kind of dumb. I mean, you almost don't need the picture, because what's the chart on Rn? We just use the identity, right? So what's the local coordinate representative of this chart, as in John Lee's notation, phi hat? It's equal to what? Yeah, the identity, which we don't really need to do, composed with phi. Composed with what? Phi 2 inverse. Is phi 2 inverse composed with phi smooth? It is. It's a transition function. By assumption, it's smooth. You see? So by the definition that we've already given, every coordinate chart is itself a diffeomorphism from its domain to an open subset of Rn. Which means that we talked about the open submanifold, like an open manifold. We said if M is a manifold, if you take any chart domain U, it's itself a manifold of the same dimension. In fact, it's diffeomorphic. And the diffeomorphism, well, anyway. I guess the diffeomorphism, I should say, between, well, this doesn't quite do it, does it? This just proves that U is diffeomorphic to Rn, doesn't it?
Is that every open chart in a manifold?
Yeah, see, this hasn't quite proved it. My bad. What's that?
You said every open chart in a manifold is diffeomorphic?
Well, what I'm trying to say is every chart in a manifold without boundary is a diffeomorphism to Rn. I mean, I guess what I've proved here is it's a diffeomorphism to phi of U, But there are other theorems that say that if you have an open subset of Rn, that itself is diffeomorphic to a ball, which is then diffeomorphic to all of Rn. It's not quite what I was trying to prove. I'm sorry, guys. What's up?
Every open subset of Rn?
I think it has to be connected.
You said here M is
Yeah.
diffeomorphic to U.
All right, so let me, what's that?
Here you said M is diffeomorphic to U.
I do think that's true, but I don't think I've proved it here. I need well, I think the way to do it is, and I hate to use this letter again, but this guy, where it's just so you can prove that mapping is a diffeomorphism because it's smooth with smooth inverse. So a few things more to tell you guys about here, and then I think I will not get the tangent spaces today, sadly. But mostly what I have to tell you about in what follows is mostly like kind of show and tell kind of stuff. So I'll just read it in the interest of us not being here too long. And well, anyway, so here we go. Let me get to it. So first of all, properties of diffeomorphisms are really nice. Like the composition of diffeomorphisms is a diffeomorphism. Every finite product of diffeomorphisms between smooth manifolds is a diffeomorphism. Every diffeomorphism is a homeomorphism and an open map, whatever that means. The restriction of a diffeomorphism to an open submanifold, with or without boundary, is a diffeomorphism onto its image. Diffeomorphic is an equivalence relation on the class of all smooth manifolds, with or without boundary. This is proposition 2.15. I will probably make this the proof of it, like one of the problems in the next homework set, because I think that one should be pretty easy, but also like nice because it'll help kind of like make sure you guys are completely understanding diffeomorphism. The next one here, theorem 2.17, it says a non-empty smooth manifold of dimension m cannot be diffeomorphic to an n-dimensional smooth manifold unless m equals to n. So, there is the dimension of a manifold is a diffeomorphism invariant. And if you look at the proof, what he does basically is just, supposes he has a diffeomorphism from m to n, and then if that's the case, that gives you a local coordinate representative, which goes from an open subset of Rm to an open subset of Rn. At which point he quotes something from an appendix where it's proved that Rm is homeomorphic to Rn only if and only if m is equal to n. This is actually a kind of difficult thing to prove in topology. Showing that Rn and Rm are not homeomorphic is a surprisingly difficult thing in topology, because they have the same cardinality. So like all of your basic set theoretic weapons against it fail. It's something deeper. Just a comment there. Theorem 2.18, it says that if you have m and n are smooth manifolds with boundary, and f goes from m to n a diffeomorphism, let me write this one up. This one's worth writing, because there's not much to write. Things work just like we saw in complex. It's like if you got a smooth mapping, smooth diffeomorphism from m to n, then f of the boundary of m is equal to the boundary of n. So a smooth diffeomorphism of manifolds with boundary will map the boundary to the boundary. So that's very, very cool. And also, it's also true that if you restrict it to the interior, you get a diffeomorphism from the interior to the interior. So there's that.
Which one is that?
That was theorem 2.18. The last things I need to tell you guys today, I just want to make you aware of something called the support. So like the support sup. So this is from page 43. Sup f is the closure of P in the manifold such that f of P is not equal to 0. The closure of this is called the support of f. Here, f is a mapping from the manifold to either, well, it could be R. It could also be or a vector space. So it could be a real valued or a vector space valued map, right? You can define the support, all right? So the support is, basically it's a set on which that contains all of the points. The support of f contains all of the points in the domain on which the values of the function are non-zero. That, it turns out, leads to, there's a whole interesting discussion here that is really beyond where I'm taking this course, but we need to be aware of this. So I'm just telling you the high points here, which is lemma 2.26. This is the extension lemma for smooth functions, and it says that basically if you have A is a subset of M, so this is a closed subset of a smooth manifold with or without boundary, and you have F is a mapping from A to RK, all right? A smooth function. Then for any open subset U containing A, so if this is A, so if you have U like this, all right? For any U open containing A, there exists a smooth function F tilde, which goes from M to RK, all right, such that F tilde restricted to A is equal to F. And sup, as in what's up, sup of F tilde is a subset of U. So this, what this basically says, guys, is that if we have a function on a manifold, all right, and we know that its non-zero values all happen within some closed set, all right, then we can take that function and we can extend it in such a way that it dies to zero by the time it reaches the edge of that open set. All of the non-zero values are inside that open set. See that? So this is a way we can take a function which is defined locally and extend it to be defined globally on a manifold. The way this is done is technical. It's quite technical. This was maybe the hardest homework problem I worked in grad school, actually building these functions that do this. It's subtle, but it can be done. And the details are actually, I think, in Lee. They're probably easier than whatever I did in grad school, but there's that. And then finally, last thing is theorem 2.29 is really, really cool. It says that if you have M as a smooth manifold and K is any closed subset of M, if you have any closed subset of M, like, so here's M and here's K, whatever, it's some closed subset of M, then you can write that as the inverse image under, of some smooth function. He says that there exists a smooth non-negative function f from the manifolds to the reals, such that the inverse image of 0 is that closed subset. Use 0. So that's pretty cool. If you have a closed subset of manifold, there is some function out there, some smooth function out there, which will take that closed set as its inverse image. This is kind of cool. That I'm sure will be useful for certain theoretical purposes. The proof is non-trivial, and it involves the things that I have skipped over in chapter 2 of John Lee's book. Yeah.
It maps 0 like the point?
Maps 0 like the point. This is the inverse image. So let's see here. To give you an so for example.
It's an inverse image, not inverse function. It's a pre-info.
So for example.
Okay, because I was going to say, how can you have like an inverse function or a set with more than one value that maps to one value, but it's a pre-image?
Yes. So for example, here's a closed subset called ON. So this is A in 3x3 matrices, such that A transpose A is equal to I. No, scratch this. Let me maybe easier here. SLN, SL3 maybe. So A in 3x3 is such that the determinant of A is equal to 1. That is a closed submanifold of R3x3. Because, in fact, if we take f of A equal to the determinant of A minus 1, then f inverse of 0 is exactly SL3. It's the set of all the matrices whose determinant is 1. And you can, well, we will talk about the theorems in here, which actually do the rest of the job to prove that it's an honest to goodness submanifold.
Couldn't you just say f(1) equals 0? Or you mean just?
Well, I'm trying to illustrate the theorem, which was inverse image is 0. So I subtracted 1 so that when this is 0, it makes that 1.
Okay, because the inverse image of 0 would just be that set in this case.
Yes.
Okay.
Right.
Yeah.
Yeah. That's a pretty cool theorem. Anyway, I will shut up. Next time, we will do tangent spaces.
I
So
understand.
my apologies, I did not get further today, but you know what? One day at a time. So it's all good.